Thanks for having me here. What I'd like to try and cover today is a bit of a sort of a case study of what has happened when some of the requirements from the OEMs are pushed down to the tier ones, and how we as suppliers try and help the tier ones as the tier ones push that extra responsibility down to us. Aversan in general is more of an engineering services and a product company, but our products are not the physical, tangible things. We don't have a production line, things like that. Our products are documents, data, intellectual components. So even though a lot of the discussions that have happened today seem to be more along manufacturing and getting that particular product out in production lines, there's a lot of things that have been said today which resonate and have similar lines up even when you are producing a document. It's basically doing the investment up front, planning how you're going to execute and deliver, and then finally providing that to the end customer. So I'm going to cover three areas where we have performed this. The E350 program is the example I'm going to be using. With the areas that we took a look at in terms of process were test procedure process of how test procedures are written, executed, and results collected, the test venue that's used to actually execute the test, and any forensic activities used to analyze after the fact events. So the example program is the A350. A350 is was awarded to Honeywell. Larger packages were provided to Honeywell so that the supplier can perform any internal trade-offs and optimizations without having the OEM do that for them. The Airbus is expecting a more mature product to be delivered in return. The award to Honeywell consisted of 5 main work packages: the bleed air system, the air conditioning system, cabin pressure control, ventilation control system, and supplemental cooling system. Since Honeywell got these larger work packages together, they're all operating somewhat independently, and Aversan as a supplier, we went in and got part of the air conditioning system system verification effort. So that's the subsection that I'll be targeting. So the work package 2, which is the air conditioning system, is a DAL-B system, has 4 subsystems associated with it: air generation, temperature control, conditioned air system, and electric heaters. The entire ship set for this system touches over 40 LRUs, and there are a couple of core LRUs that are specific to this particular subsystem. And part of this system is that it's highly reconfigurable. So it's not that this one box only does this one function, but they're trying to accommodate for different configurations of the end customer requests on the aircraft. Temperature control system is primarily the biggest reconfigurable item. The other complexity in the system is redundant architectures, where the controllers have dual lanes to increase dispatch time or in-service time. So since the larger scope of work was given to Honeywell, in turn, the supplier is expected to do more in return. So they do the internal trades to optimize between the subsystems. It's no longer going to be different suppliers trying to negotiate back and forth through Airbus to figure out how to best solve something. The LRU integration, previously the airframers had their own system integration lab. Every supplier provides their individual LRU. The expectation now is that Honeywell takes care of the integration of their LRUs, and then a more mature system in its entirety is delivered up to Airbus. And the system requirement verification is more formalized. Historically, at the system level, the system engineers had their requirements. They went to their test bench, they did some manual test documentation, passed to make sure everything was working properly. But the systems are much more complex, there's much more functionality built into them, and there's more formalization to the verification process now. And all of this together is so that there's a more mature product delivered to the customer. The system complexity, newer technologies involved, digital communication buses. The systems are both compact and distributed and redundant. Compact in that there's more functionality in a single box. So whereas before a box had a single function that it performed, now that it performs 4 or 5 functions. And the whole goal of doing the verification is to try and capture the defects as soon as possible, as early in the life cycle as possible. The later that the defects escape, the more cost it's going to be to go back and do that fix. So the question is the supplier ready for this? And basically, this was a very large program that Honeywell undertook, and they really needed a paradigm shift to get out from where they were to where they had to be. Previously, it was 1 or 2 system engineers that took care of the main requirements, and they kind of had a handle on it. Now there's a whole team of system engineers, and they have to communicate and get their requirements in sync and in line for the downstream. Previously, they used to decompose the system and test the system in isolation. So they took one subsystem at a time and tested it and said, yeah, it seems to work properly. And then integrating it together was sent back up to the airframer in their lab. Because of the volume of requirements and the complexity of the system, the verification had to be more formalized and automated. You can no longer have somebody sitting in front of a manual panel flipping a few switches back and forth and say, yeah, the function is working. The system tests will be repeated. We have run the test suite that we have right now multiple times over and over. We've had 4 separate deliveries for flight and ran safety of flight tests. So if anybody tells you you're only going to run a test once, they're kidding you. It's not going to happen. And the other thing that we want to try and achieve is to report as much data as possible. Historically, again, somebody sitting in front of a test bench, they're going to be flipping switches. They'll only notice things if they're really looking for it. And if the more complex system it is, the more data there is, you can't possibly see everything. So we try and log as much data as we can so that if something does happen, we can go back and figure out why. Or even if we didn't notice it, we can go back historically and say, well, we saw this in flight test when you ran that in your lab. Did you see the same sort of event? We can go back and pick up on that. So the way that we moved across there is test procedure documents, historically just written as a document in Word. And in the end, when you put something just in a Word document, it's essentially dead. The only way that the information gets out of that document is somebody reading it. You have to start looking at the flow of that information that's going to be going, who else is going to be using it. So I still see specifications where they put a Word, even if they put in a Word document, they put a table, which is a graphic image that you can't even search or copy or paste, and that kind of thing has to change. So you have to think about the data that you are putting in. That's not the end of the data. It will live further. So we went from documenting our test procedures in a Word document to an XML-based format, which then we can then leverage and build subsequent processes. Manual test panels and result collection has been replaced with an automated test execution facility that we can run 24/7. And right now, we're going to be gearing up for our sort of certification run. Our expectation is that this is going to take 2 weeks of running 24/7 to run full test suite. Historically, limited supplemental data, basically limited by the person sitting in front of the test bench and reporting what they observe, and they have to be very astute to notice certain things or to expect certain things. Now we have extensive data logging, so even if they didn't notice it when it happened, we can go back and see it, look at things forensically. Instead of doing, historically, again, these subsystems, they broke down in smaller pieces and using things in open loop just to check general connectivity. We are now trying to put more LRUs together, trying to do more integration up front, and doing everything in a closed loop manner so that it is more representative of what is expected to happen on the aircraft. So test procedures, as I mentioned previously, office productivity tools, so Word, Excel. It's great for initially capturing things. Excel is a little better because you can have some sort of life of the data after that. but after that is dead. If you compare it to, let's say, the things like in CAD, right? When they went from paper to computers, okay, that was the first shift. It was just straight on paper. The only way out of that is reading it, and somebody has to translate. Going into a CAD system, all of a sudden you can get other things like the modeling, the production, things like that. The same thing applies for a lot of the other data that is generated as part of testing. Test procedures were either manually executed, or if they are automated, the script was considered to be the procedure. Once you start doing manual translation, there's going to be discrepancies. If the procedure changes, or if the script has to change to satisfy what's needed, that has to be flowed back to the procedure, so keeping things consistent. And in cases where it was considered that the script is essentially the procedure, that's only as good as readable the script is. So if you are using some sort of scripting language that isn't quite clear, it could get quite complex and you might lose the intent of what are you actually trying to test. So the takeaway here is that plan that the data that you're going to be using for your test procedure is not the end of where that data is going to live. It should live further. So test procedures, we're capturing them in an XML document, so basically it gives you a form-based entry. It keeps the test procedures consistent between developers. There's a team of 20 plus developers, so this method keeps things in a very regular manner. We provide high-level constructs or high-level steps. Stimulus response testing is essentially stimulated this way. This is what I expect to get back. So that's what the test procedure is structured at. From the XML, because it is a very structured way of documenting the procedure, we can then automatically generate a script out of it. And the script that we generate could be targeted for any venue that you want. We just put in the appropriate translator. Then the results that we collect, we also transform that from an XML and tie it back to the original procedure. So essentially we can see the procedure and the results online. So that kind of, similar to some of the other thoughts that were put forward, is that we're looking at how are we going to deliver the end product, which is the test results, and we're trying to establish a process of that's how we're going to get there. The benefits of this, test procedure is independent of the test venue, so there's a progression path. Essentially, you write your procedure, and if your test venue goes down, or if there's technology change in your test venue, the procedure is still valid. You just need a new translator to put it into whatever target context you have. As an example here is the scripts that we're generating is for a scripting language, which is a custom in-house language developed 20 years ago. There's so much investment in all of the test programs that they have, these scripts that are written, they can't afford to change and go to a newer technology. So this decoupling of the procedure from the underlying technology leaves you open to having progression path going forward. So it's a cost of ownership for long term. And the other ones I think I've already touched on. So automated script generation, so we can guarantee that the script and the procedure are 100% consistent. And from the XML side of things, because it's a very structured approach, we can start pulling out information. Recent thing, post-analysis, saying, well, how many signals have we actually covered all of the signals that are coming out of the system? I could easily go in and query all the XML documents and say, these are all the signals that we're touching, these are the different values that we're verifying out of the entire test suite. Test venue. So, as mentioned before, manual test panels were used. This is another one of the points that was brought up earlier. Short-term vision, don't spend any money now. So essentially what they do is say, well, electrical engineering created this test panel for testing their LRU, use it for system testing because I don't want to design anything new, I don't want to build anything further. So short-term savings, long-term, it kills us. And in fact, for this system, we have over 20 actuators, over 100 sensors, and trying to do that in any kind of open loop manual way is just not possible. So this is another one, again, hitting on some of the points brought up earlier, is that we try and identify what we need first and get the machine later. As opposed to here, we got the machine first, and then we said, well, doesn't do what we need. So the shortcomings of the original proposed venue, there's verification gaps. If the planning was done to say this is the scope of testing that we needed, there was obvious gaps of what the venue could do and what it couldn't do. The cost and schedule implications, okay, great, you got this test station in immediately, but guess what? A month or two later, when it actually comes to running these, it's going to kill us. And their solution will run 3 shifts, and that's essentially their short-term solution. And as well, on this end, Airbus came back and said, we want you to have a more fully integrated system as opposed to a single-sided or a subset of LRUs. So the first battle was convincing upwards to the program management. This has to change. You can't get there from there. And even though most benefit is achieved if you do it early in the life cycle, it's never really too late to do some kind of change. So even if you are down a certain amount way down the path, you can always identify key areas where you can make some sort of change and get some initial benefit out of it. Along with the convincing of the program to do it, the typical question, do you need it or can you do it manually? And, well, yes, we can do it manually, but every time you do it manually, there can be an incurred cost. And trying to do something in a closed-loop environment where you need certain things done at precise times in the test, doing it manually becomes more and more cumbersome. So even though some of these functions that are being asked cost a bit more upfront, at the back end, there's a lot of benefit. So 2 particular examples, one that worked and one that didn't, is we were battling to have capability for short power interrupts for these LRUs to test warm starts, cold starts, and how the system behaves. In hindsight, the system had a lot of problems recovering from those warm starts, restoring the right system variables, keeping track of where valve positions were. This paid off big time. Another example is the venue D scope. We had stepper motors, and we wanted fault injection for electrical faults on both coils. They said, well, do you need it on both coils? Can you do it with only one? Because that would save us some costs. At that point, I said, okay, fine, I'll back off on that one. In hindsight, probably a bad choice because late in the program, we found out that if both coils had a problem, the wrong fault was enunciated. So, yes. Not an approved equipment list. We've always done this way. This is the other comebacks. In summary, if you do not change and keep pace with what is out there, then you're going to guarantee obsolescence. So right now, the test venue, we built it using a lot of the pieces that they already had. It wasn't a complete design from scratch, but it was basically, what are you doing in the different places? How do we put it together to get what we need? So now we have a system with a representative set of LRUs, a dual-sided system that talks to one another, reconfigurable LRUs for some of those instances that are throughout the aircraft, automated fault injection, and fully automated repeatable results. So we have had cases where one-off events, it happens in a test once if you run it 100 times. Well, to catch it again, you're going to have to run it 100 times more. And we have come across those particular cases. Batch execution system to automatically queue up all the tests for all the users, 20, 25 testers competing for one venue. This allows us to put a prioritized batch for their submissions. And the automation, we're trying to do all the mundane work through automation and use the people power, use the brain power where it's really value added. Test data. So previously, recording is only as good as what the tester knows to look for. An experienced tester is obviously going to see more than a less experienced tester. Real-time events may not even be observed if there is a glitch, or if they did observe it, they may not capture all the data, and there's not enough data to understand what happened. So now we are doing as much real-time data logging, digital data buses, trying to stream everything to disk, offline analysis for analyzing the one-off events, generating additional plots of key pieces of data, and historical investigation. As I mentioned, an event happened in another lab or on an aircraft, we can go back to a similar scenario we had that we ran maybe a couple of weeks ago, and we can go into that data even though we didn't look at it at the time. So increased reliability, repeatability, and accuracy. The decreased cost and shorter time to market. We've turned around from a software release to a safety of flight. Our first go-around was 6 weeks from the first software delivery to the A350 first flight. The turnaround for subsequent executions, our analysis portion is about 2 weeks, including including execution. So software release to on-aircraft flying is about 3 weeks. So a snapshot of where we are in on this program. We've been working this for over 4 years. Our efforts have identified over 2,000 problem reports. So that's all before they got out of the building, which is a good thing. Of the over 2,000 we raised, there are about 5% that were not real problems. So actually the balance, there's a lot of real things that were identified. One of the comments engineers made is that we're finding problems that usually surface several years into service. So the more maturity, again, that we deliver upwards is going to save in the long term. As I mentioned, 6 weeks for the first iteration code release, the first flight. Other programs, I know that's gone into the months. And the extent of the testing was significantly less than what was done at this program. And we're currently working towards a certification or a qualification test run in the next couple of weeks. And for the Airbus first flight, the email that we got from the design office is that it worked as expected, no surprises. We just have to sit back and watch it work. Summary of Aversan.